All right, so page 629, section 10.3. We are looking at separable differential equations. We've actually already talked about this topic a little bit. Do you remember when we did the slope fields, the direction fields? We had a separate handout that had come from AP because in all the years that I have been teaching AP Calculus, that is the only topic that they have added to the list of topics that you should cover in this course. And they added it several years back. And with the exception of maybe 1 year, it has been on the AP Calculus exam every year as an FRQ because it's a new topic. When it is an FRQ on the AP exam, every time up to this point anyway, the top of the problem would be a slope field worth about 2 or 3 points. There might be like a little B part where they ask you something about the slope, like where would the slope be, positive or 0 or something like that. But then the bottom of it, the last 6 points, have always been a separable differential equation. So I love it that we cover this lesson at the end of the year where it's fresh in our mind for the AP exam, because we have a high probability of seeing this as one of our FRQs, and if we did, it would be 6 of the 9 points. So that should be like an ace in the hole for us, okay? So on page 629, they tell me that we've looked at first order differential equations from a geometric point of view when we did those direction fields, those slope fields. So let's look at them from a symbolic point of view. And again, that's why the two ideas are paired together in an FRQ on the AP exam. It would be nice to have an explicit formula for a solution of a differential equation. Unfortunately, that's not always possible. But in this section, we're going to look at certain types of differential equations that can be solved explicitly. And those are separable differential equations. Now, a separable equation is going to be a first order differential equation that can be separated. Back in 410, they defined a differential equation for us. They told us that it was just an equation that involved the derivative of a function. All right? So these are the steps that we want to follow for the separable type of differential equation. Number one, if they don't give me the derivative in Leibniz notation, dy dx, like maybe they give it to us as y prime, the first thing I'm going to want to do is rewrite it as dy dx. I'm going to treat that dy dx kind of like we did with the differentials, where I can think of it as a legitimate fraction that can be broken apart. So step number two, I'm going to get all of my x terms on one side and put the dx with it by moving it over, multiplying by it, whatever I need to do. And all my y terms on the other side with the dy. I cannot integrate x and y at the same time on one side. I need to separate them. I need to get all of the x's on one side and all the y's on the other side, and then I'll be able to integrate in terms of whatever variable I'm working with. All right, so once we've separated all the x's on one side with dx, all the y's on the other side with dy, then we can integrate both sides. I'm going to get an arbitrary constant on both sides. There's no need to write it on both sides. Because if I have a constant on one side and then I subtract it over to the other side, I'd have a constant minus a constant, which is still just a constant. So they don't require me to write that and show that work. Then, if they happen to give me any initial conditions, they don't always do that, but if they happen to give me any conditions, I could plug those in, and that would enable me to solve for C, so I wouldn't have the arbitrary constant anymore, and I would have a particular solution for that individual situation. Sometimes they do that, sometimes they don't. So let's look at an example. Example number one, they tell me your derivative, dy dx, is equal to 6x squared over 2y plus cosine y, and they want me to solve the differential equation and go back to just plain y. Get rid of the derivative, okay? So we know that to undo a derivative, we integrate, but my problem would be if I came over here and tried to integrate this as it was, I can't integrate with x and y at the same time. It's got to be in terms of one variable. So I want to separate this. So since it's already written in terms of dy dx, then let's come down to step number two. Let's get all of our x terms on one side with dx, all the y terms on the other side with dy. So I'm going to multiply both sides by the dx, treating this like a fraction where it's two separate pieces. I could multiply both sides by dx, and that would give me 6x squared dx on my right-hand side. Then I'm also going to multiply both sides by 2y plus cosine y, so that'll give me 2y plus cosine y dy on the other side. Another way for this particular problem that I could have looked at it is I could have cross multiplied. I won't always be able to do that, but in this case I could have. All right, so then we want to integrate both sides. So we'll go through what you do to one side, you do to the other. It's a legal move. What is the integration of 2y?
Y squared.
Yeah, 2y squared over 2, so y squared. What's the integration of cosine?
Sine.
What's the integration of 6x squared?
12. X 12. Yeah, x squared, sorry. Third. I know, I'm done.
What is it?
Third, 2x cubed, yeah.
So we'd have 6x to the third over 3. So yeah, you could reduce that to 2x cubed. All right. So we could go through and simplify the 2's here to just have y squared, and simplify the 6 over 3 here to just have 2x cubed. And again, we did not need an arbitrary constant on both sides. It does not matter which side you put it on. I just put mine on the right. Now, if they had not given me an additional piece of information here, that would be my answer. All right, so let's deal with y1 is equal to pi. That means that when x is equal to 1, y is equal to pi. So I'm going to put 1 in for every x and pi in for every y. When I do that, the only unknown then will be c, my arbitrary constant, and I'll be able to solve for it. So what's the sign at pi? 0. So I'll have pi squared plus 0 is equal to 2 plus c. Subtract that 2 from both sides, and c is pi squared minus 2. So let's come down here to the solution that we had gotten, and we'll replace c with what we just found. It was equal to pi squared minus 2. So there's our solution. All right, let's look at another one. Example number 2. They ask us to solve the equation y prime is equal to x squared y. Y prime is equal to x squared y. All right, so example 2. Step number 1, we want to write the derivative using Leibniz notation because this time they gave it to us as y prime. So I'm just rewriting that with different derivative notation so that I'll be able to work with it as a fraction and separate it. So number 2, let's get all the x terms with dx on one side and all the y terms with dy on the other side. So you can see for this one, I couldn't just cross multiply like we did last time. I'm going to multiply both sides by dx, and then I'm going to divide both sides by that y. All right, so now I can integrate both sides. What I do to one side, I do to the other is a legal move. What's the integration of 1 over y? ln absolute value y, right? Integration of x squared?
X cubed over 3.
X cubed over 3. All right, now they did not give me an initial condition this time. So since they didn't, this could be the answer for my original equation. However, for AP, what they typically will ask us to do is give our answer explicitly. Remember when we did implicit differentiation, we talked about that was when y was inside the problem when you were taking the derivative. Typically when we have the original equation, it's y equals something and we just take the derivative explicitly. So that's what they're asking for here. Hey, since we gave you the derivative explicitly, we want you to give the answer explicitly as well, which basically means we want you to tell what y is equal to. We don't want it embedded into the equation. So that will make this one a little more challenging because we need to get the y out of here. We need to get it outside by itself. So I need to get rid of that ln. What's going to undo an ln?
E.
An e. So let's go in and insert a base of e on each side. That's why we had that whole section in Chapter 7 about exponentials and logarithmics even when we weren't doing derivatives, because the basics of those things show up in so many other places. So our e and our ln will cancel each other out and leave us with just the absolute value of y. And then over here we've got e to the x cubed over 3 plus c. Now, let's hang on here for just a second. Remember, you have that rule that says when your bases are the same and you're multiplying, you add your exponents, right? Like if you had x to the second times x to the third, that's going to be x to the fifth, right? Bases are the same, multiplying, add your exponents. The reverse of that is also true then. If you had x to the fifth, you could rewrite that as x to the third times x to the second, right? So it's the same idea here. I could rewrite this exponent where I have two quantities that are being added, where I rewrite it with their bases the same and them being multiplied. What's more natural for us is to go from this step to this one, where we would say, okay, my bases are the same and I'm multiplying, so I'm going to add x to the third over 3 plus c. But you can see how I could undo that by using the converse of that popular property that we've always used. Why would I want to do that? In this particular problem, they did not ask me to find an initial condition. But if they had, and I'm actually going to have to solve for c, it's going to make it so much easier if I have that as a separate piece than if it's up here in the equation. And so that's why I did that extra step there for you. Okay? All right, how do I get rid of the absolute value?
Absolute value the other side. Yeah.
All right, when we have an absolute value equality, remember we take what's inside the absolute value and we set it equal to plus or minus what's on the other side. So that's like if you have the absolute value of x equals 2, then x can be a positive 2 or a negative 2, right? Take what's inside the absolute value and set it equal to a positive or a negative of what's on the other side. Now, that's going to be my answer, but there will be times that they'll give me extra information that would help me limit that. For instance, they might from the very beginning tell me that y is greater than 0 or y is less than 0 as part of my problem, so that I know when I get down here whether I want this to be the positive or the negative. Sometimes by the point that they give me, if they give me an initial condition, sometimes with the value that they give me to plug in and solve, then I can tell, okay, hey, since they had me plug in a positive y value, then I know y is supposed to be positive in my equation. So I don't need the plus or minus for what y is equal to. All right, so here is our homework for tonight on pages 634 to 635. We're doing 1 through 13, every other odd, 3, 16, challenge 33.